Part 1 Introduction. A revolution in the construction industry. For decades, buildings around the world have been no primaries as massive consumption of electricity every day. Millions of residential towers, office buildings, shopping malls, hospitals, hotels, and factories rely on continuous supply of energy to keep their operations running. Air conditioning system cool entire skyscraper, elevator transport thousands of people between floors, lighting illuminates every room, and countless electronic devices operated around the clock. Behind the comfort and convenience of modern life lie an enormous demand for electricity. Most equips had traditional supplied by national power grids powered by fossil fuel. Today, the construction and building sector is recognized as one of the world's and number 39 as largest energy consumer. According to international study, buildings account for approximately 35 to 40% of global energy consumption and are responsible for a significant share of carbon dioxide emissions. Every kilowatt-hour of electricity generated from coal, oil, and natural gas contributes to greenhouse gases emissions, accelerating global warming and climate change. As cities continue to expand and population grow, the demand for electricity is expected to increase even further, placing enormous pressure on both energy infrastructure and the environment. This growing challenge has forced architects, engineers, and urban planners to rethink the traditional role of building. Instead of designing structures that simply consume electricity, a new generation of architects is creating buildings capable of producing their own clean energy. This marked the revolutionary construction industry, transforming buildings from passive energy user into active energy producer. The concept may sound futuristic, but is already becoming reality in many parts of the world. Advanced and renewable energy technology have made it possible for modern buildings to generate electricity through a variety of innovative methods. Solar panels integrated into the rooftop and glass facade capture sunlight throughout the day. Small wind turbines installed on rooftops harness the power of natural airflow between skyscrapers. Some buildings recover heat from the surrounding environment to generate renewable energy, while others collect rainwater to improve energy efficiency and reduce resource consumption. Even more remarkably, emerging technology can convert the vibration created by human footsteps into small amounts of electricity, allowing busy public spaces to generate renewable power simply through everyday movement. As these technologies continue to improve, buildings are beginning to function like miniature power plants. Instead of relying entirely on traditional electricity supply, they can generate a significant portion of the energy needed for lighting, ventilation, heating, cooling, and daily operation. Some highly advanced buildings are even capable of producing more electricity than they consume, allowing excess energy to be fed back into the public grid to support nearby communities. This not only reduces operating costs, but also increases energy independence and improves the resilience of cities during power shortage or emergency. Beyond the economic benefits, solar power buildings represent an important step to a more sustainable future. They reduce greenhouse gas emissions, lower dependence on fossil fuel, and encourage the widespread adoption of renewable energy technology. As governments around the world strengthen environmental regulation and pursue ambitious carbon neutral goals, energy generating buildings are becoming symbols of innovation, responsibility, and environmental stewardship. Today, the idea of building acting at an old power station is no longer a distant dream. It has become one of the defining trends of 21st century green architecture. Around the world, groundbreaking projects demonstrating that buildings can do much more than provide shelter. They can actively produce clean energy, protect the environment, and reshape the future of sustainable urban living. As technology continues to evolve, the buildings of tomorrow may no longer be remembered simply for their higher appearance, but for their remarkable ability to generate a very energy that powers modern civilization. Part 2. Why a building needs to generate their own electricity? As the world's population costs continue to grow, so does the demand for electricity. Every year, millions of new homes, office towers, factories, hospitals, schools, and commercial centers were built to accommodate a pending city and rising living standards. Along with this rapid urban development comes an enormous increase in energy consumption. From air conditioning system and elevator to computer, lighting, and electric vehicle and smart appliances, modern life depends on a constant and reliable supply of electricity. Experts predict that global energy demand will continue to rise for decades, placing unprecedented pressure on existing power grid. For more than a century, much of the world's electricity has generated by burning fossil fuels such as coal, oil, and natural gas. While these energy sources have fueled economic development and technological progress, they have also produced enormous amounts of carbon dioxide and other greenhouse gases. The emission trap heat in the Earth's atmosphere, contributing to global warming, rising sea level, more frequent extreme weather events, and gradual destruction of ecosystems around the world. The environmental cost of traditional electricity generation had become one of the great challenges facing humanity in the 21st century. This growing crisis has inspired architects, engineers, and environmental scientists to rethink the role of building in the global energy system. Instead of designing structures that simply consume electricity, they are developing buildings that can actively produce clean, renewable energy while minimizing waste. This represents a major shift in architectural philosophy. Today, successful buildings are no longer judged solely by the appearance, height, or functionality. Increasingly, they are evaluated by how efficiently they use resources, how much energy they can generate, and how small the environmental footprint is. The goal is to transform every building into a self-sustaining energy system. Rather than relying entirely on electricity supplied by distant power plants, modern buildings can harvest energy directly from natural resources available on site. Solar panels capture sunlight throughout the day. Rooftop wind turbines generate electricity from moving air. geothermal system utilize the Earth's natural heat. An advanced energy management system optimize power consumption in real time. Together, these technologies enable buildings to produce a significant portion or even all of the electricity they require for daily operation. The benefits of solar power buildings extend far beyond lower electricity bill. One of the most significant advances is dramatic reduction in greenhouse gas emissions. Every unit of renewable electricity generated by a building reduces the need for electricity produced by fossil fuel power plants, helping to combat climate change and improve air quality. At the same time, building owners can save substantial amount of money and reducing their dependence on the public electrical grid. Over the lifetime of a building, these savings amount to millions of dollars, making renewable energy investment economically attractive as well as environmentally responsible. Another important advantage is its energy security. During natural disaster, extreme weather, or unexpected power outages, conventional buildings often become completely dependent on emergency generator or external assistance. In contrast, buildings equipped with renewable energy systems and battery storage can continue operating independently for extended periods. Hospitals, emergency response center, airports, and data centers particularly benefit from this level of resilience, ensuring that essential services remain available even when the main power grid fails. Self-generating buildings also place less strain on national electricity network. When thousands of buildings produce their own electricity, the overall demand on the grid decreases, reducing the need to construct traditional power plants and expensive transmission infrastructure. Some advanced buildings can even generate surplus electricity and feed it back into the public grid, effectively becoming small renewable power stations that support surrounding community. This decentralized approach creates a more flexible, reliable, and sustainable energy system for entire city. Beyond the technical and financial advantages, energy-producing buildings represent a new vision for sustainable urban development. They encourage innovation, promote cleaner technology, and demonstrate that economic growth and environmental responsibility can coexist. Around the world, governments introducing energy efficiency standards and carbon reduction targets make solar power building an increasingly important part of future construction process. Many experts believe that the coming decades, the ability to generate renewable energy will become a standard feature rather than a luxury. Thus, modern buildings that are now expected to include internet connectivity, efficient insulation, and smart technology. Future buildings may all be designed to produce their own electricity. In the new area of green architecture, every rooftop, facade, and structure surface and potential become of energy source, helping cities become cleaner, more resilient, and better prepared for the challenges of the future. Part 3. The Edge, one of the smallest office buildings in the world, one of the world's most outstanding examples of sustainable architecture is the Edge, an innovative office building located in Amsterdam, the Netherlands. Widely recognized as one of the smartest and most energy-efficient office buildings ever constructed. The X has become an international benchmark for green building design. Instead of functioning as traditional office towers that simply consume electricity, it was designed to produce clean energy, minimize waste, and uses advanced digital technology to optimize for every aspect of its daily operation. One of the building's most impressive features is its extensive solar energy system. Thousands of high-efficiency photovoltaic panels are installed across the rooftop and integrated into the parts of the building exterior. Throughout the day, these solar panels capture sunlight and convert it directly into renewable electricity. The energy produced supplies a large portion of the building's daily power needs, including lighting, elevator, heating and cooling system, ventilation equipment, and office electronics. By generating much of its own electricity, the X significantly reduces its dependence on the public power grid while lowering carbon emissions and operation costs. However, what truly makes the X exceptional not only the amount of electricity it generates, but also the way it uses the energy. The building is equipped with one of the world's most advanced smart sensor networks. Thousands of sensors are installed throughout the offices, meeting rooms, hallways, and sales spaces. The intelligent devices continue to monitor occupancy, temperature, humidity, air quality, and lighting conditions in real time. Whenever an employee enters a room, the sensors immediately detect their presence. Light automatically switch on, adjust their brightness according to the amount of natural daily light available. At the same time, the climate control system regulates the room temperature to create a comfortable working environment. Once the room becomes empty, unnecessary lighting and air conditioning are automatically reduced to turn off. As a result, electricity is consumed only where and when it is actually needed, eliminated much of the energy waste commonly found in conventional office buildings. The building also makes excellent use of natural light. Large glass façades allow sunlight to reach deep into the interior, reducing the need for artificial lighting during daytime hours. Smart lighting systems constantly measure outdoor brightness and automatically adjust indoor illumination to maintain ideal working conditions while using the least possible amount of electricity. All of this technology work together to an intelligent energy management system that continuously analyzes data and optimizes building performance. Every decision, from adjusting room temperature to controlling lighting, is designed to maximum comfort while minimizing energy consumption. This combination of renewable energy generation, artificial intelligence, and smart automation allows the Earth to achieve an extraordinary level of energy efficiency that far exceeds that of most traditional office buildings. Today, the ice stands as a symbol of the future of sustainable architecture. It's proof that modern building can be both technologically advanced and environmentally responsible, demonstrating how clean energy and intelligent design can create healthier workplaces while significantly reducing environmental impact. Past 4. Bahrain's World Trade Center, the skyscraper powered by giant wind turbines, where many modern buildings generated electricity from sunlight. The Bahrain World Trade Center demonstrates that wind can also become a powerful source of renewable energy when architecture and engineering work together. Located in the heart of Manama, Bahrain, this remarkable skyscraper is widely recognized as one of the world's first large commercial buildings to integrate utility-scale wind turbines directly into the architectural design. Rather than treating renewable energy as an afterthought, the building was conceived from the very beginning as a structure capable of harnessing the natural power of the wind. Completed in 2008, the Bahrain World Trade Center immediately attracted global attention because of its distinctive appearance. The complex consists of two elegant cell-shaped towers rising approximately 240 meters above the city skyline. Inspired by traditional sail of the Arabian Darbow, the tower reflects Bahrain's rich maritime heritage while also serving a highly practical engineering purpose. The unique curved forms are not simply architectural statements, they were carefully designed to manipulate wind flow and maximize renewable energy production. Connecting to the two towers are three enormous horizontal axis wind turbines, each measuring approximately 29 meters in diameter. Suspended high above the ground on large steel bridges, these turbines create one of the most recognizable features of the building. Unlike conventional skyscrapers that rely entirely on the electricity supplied by thermal power plant, the Bahrain World Trade Center is capable of generating part of its own clean energy by capturing one of the region's most abundant natural resources, wind. The building's innovative design takes fully advantage of the prevailing wind that's blowing across the Persian Gulf. Engineers carefully studied local wind patterns before construction began, using advanced computer simulation and wind tunnel testing to determine the optimal orientation of the tower. The two sail-shaped structures are positioned so incoming wind and naturally funnel into the open space between them. As the wind passes through the narrowing gap, its speeding increases due to the venturi effect, a well-known principle in fluid dynamics where air accelerates when flows through a confined passage. This natural acceleration allows the wind turbine to rotate more efficiently than they would if they were installed on conventional rooftops or in open field. Instead of fighting against the forces of nature, the building works in harmony with them, transforming architecture into a central part of the energy generation system. Each of the three turbines operates independently, continuously converting the kinetic energy of moving air into electrical power. Whenever wind conditions are favorable, the spinning blade drives electrical generator that produce clean, renewable electricity without burning fossil fuel or releasing greenhouse gases. The electricity generated is supplied directly to the building, helping power common area lighting, elevator, ventilation system, and various shared electrical facilities. Although the wind turbines do not produce enough electricity to operate entire skyscraper, they are capable of supplying meaningful percentage of the building annual energy demand under a normal operating condition. The turbine can provide approximately 11 to 50% of the building total electricity to consumption. Over the course of the year, This represents hundreds of megawatt-hours of clean energy and prevent the emission of hundreds of tons of carbon dioxide that would otherwise result from conventional electricity generation. Integrating massive wind turbines into a high-rise building presents a significant engineering challenges. The turbine needs to withstand powerful wind, vibration, changing weather conditions, and continue its operation over many years. Engineer design specialized steel bridges capable of supporting the turbine while minimizing structural movement and vibration. Advanced control system constantly monitor wind speed, turbine rotation, and mechanical performance to ensure safe and efficient operation. During periods extremely strong winds or maintenance for requirement, the turbine can automatically slow down or stop to protect both the equipment and the building. Another remarkable achievement of the Bahrain World Trade Center is the way renewable energy technology become an integral part of the building identity. Unlike many sustainable systems that remain hidden from public view, the three giant turbines are impossible to ignore. Visitors and residents can immediately see the blades rotated between the towers, providing a powerful visual reminder that clean energy can become a natural part of everyday urban life. The building itself serves as an education symbol, demonstrating that renewable energy technology can be both functional and architecturally inspiring. Beyond the technical innovation, the Bahrain World Trade Center has a lasting influence on sustainable architecture around the world. Before its construction, very few skyscrapers had attempted to incorporate large-scale wind power directly into their structural design. Its success proved that renewable energy system could be integrated into high-rise buildings without compromising aesthetic, safety, or commercial functionality. Since then, architects and engineers have explored new ways to incorporate wind energy into an urban environment, drawing inspiration from the pioneering concept demonstrated in Bahrain. The project also highlights the importance in designing buildings specifically for their local environment. Rather than applying a one-size-fits-all solution, the architect carefully considered Bahrain's climate, geography, and prevailing wind conditions. The result of building uniquely adapted to its location, showing that sustainable architecture depends on understanding and working with nature instead of resisting it. Today, the Bahrain World Trade Center remains one of the world's most iconic examples of renewable energy architecture. It stands as proof that skyscrapers can become more than places to live and work. They can actively participate in producing clean electricity while reducing dependence on fossil fuel. As cities continue searching for innovative ways to lower carbon emissions and improve energy efficiency, this remarkable building continues to inspire the next generation of architects, engineers, and urban planners. Its soaring tower and giant wind turbine symbolize a future in which architecture is no longer merely a consumer of energy, but an active contributor to a cleaner, greener, and more sustainable world. Part 5. Basking over the cloud, where nature and clean energy work together among the world's most inspiring examples of sustainable architecture, like sparkle vertical on quartz, vertical forest and quartz. Located in Milan, Italy, unlike most modern skyscrapers that rely primarily on steel, glass, and concrete. Box-covered house introduces an entirely different vision of urban living, one in which nature becomes an essential part of the building itself. Covered with thousands of trees, shrubs, and flowering plants, the remarkable residential tower has become an international symbol of green architecture, demonstrating that living vegetation that can work alongside advanced technology to create healthier, more energy-efficient buildings. Complete in 2014, Bosco over the coast consists of two residential towers rising approximately 80 and 112 meters above the city. What immediately captured attention is the extraordinary amount of greenery covering the balcony. More than 800 mature trees, over 4,500 shrubs, and approximately 15,000 perennial plants have been carefully planted throughout the building. Together, this vegetation is equivalent to the ecological benefits and small forests spread vertical across the facades instead of occupying valuable land and street level. As first planned, the tree appeared to serve only a strategic purpose, transforming the tower into a large green landmark within the urban skyline. However, their true value extends far beyond beauty. Every tree and plant has been carefully selected and positioned to perform specific environmental functions that directly improve the building energy efficiency while creating a healthier living environment for residents. One of the greatest challenges faced by modern buildings is managing heat. During the summer months, sunlight striking glass windows and concrete walls causes indoor temperature to rise rapidly. Conventional buildings often rely heavily on air conditioning systems to maintain comfortable conditions, leading to enormous electricity consumption. Bosco Vertical approaches this challenge in an entirely different way by allowing nature to perform much of the work. The dense vegetation covering the balcony acts as natural protective shield against direct sunlight. Tree canopies provide shade from window, balcony, and exterior wall, preventing excess of solar radiation from reaching the building envelope. As a result, significantly less heat enters the apartment, reducing indoor temperature naturally before mechanical cooling systems are even required. This passive cooling effect rapidly lowers the demand for air conditioning during Milan warm summer, the resulting substantial energy saving. The cooling benefits extend beyond simple shading. To the natural process of proper transpiration, trees release water vapor into the surrounding air. As this moisture evaporates, it absorbs heat in the environment, producing a localized cooling effect similar to natural air conditioning. This process helps create a more comfortable microclimate not only for residents but also for the surrounding neighborhood, contributing to the reduction of the urban heat island effect commonly experienced in large cities. During winter, the vegetation provides a different but equally valuable function. The branches and foliage create additional insulating layer around portions of the building, helping reduce heat loss from the interior. Combined with modern insulation material that has high-performance windows, this natural barrier decreases the amount of energy required for heating. By By reducing both cooling needs in summer and heating demand in winter, Bosco vertical car achieve impressive energy efficiency throughout the entire year. Nature is only one component of the building. Sustainability and strategy Bosco Vertical also operates modern renewable energy technology, including solar panel and advanced energy saving system designed to reduce dependence on the conventional electric resource. The solar installation contribute clean, renewable electricity that support position of the building energy requirement while highly efficient mechanical system ensure that even every unit of energy is used as effectively as possible. Sophisticated energy management technology continuously monitor lighting, ventilation, heating, and water consumption throughout the building. Efficient LED lighting, modern insulation material, intelligent climate control system, and optimized building operation work together with renewable energy generation to minimize the electricity consumption with compromising resident comfort. Water management also plays a central role in maintaining the vertical forage. Irrigation system use treated wastewater and carefully controlled distribution network to provide a tree and plant with the precise amount of water required. Sensor continuously monitors soil moisture and environmental conditions, ensuring healthy plant growth while minimizing unnecessary water use. This is intelligent integration of technology and nature demonstrate that sustainable architecture depends upon carefully balancing multiple environmental systems. Perhaps the most remarkable contribution of Bosco Vertical ability to improve urban air quality. The thousands of trees that plant continue absorb carbon dioxide while release oxygen into the atmosphere through photosynthesis. They also capture fine dust particles, filter airborne pollutant, and help reduce noise pollution throughout the surrounding area. In effect, the building functions as a living ecosystem rather than simply a collection of apartments. The ecological benefits extend to wildlife as well. Birds, butterflies, bees, and numerous beneficial insects have found habitats among the extensive vegetation. Increasingly, biodiversity within the one of Europe busy and metropolitan area. What with one conventional urban environment has been transformed into a thriving vertical ecosystem that supports both human life and local wildlife. Bosco Vertical demonstrates important principles of sustainable architecture. Renewable energy does not always come directly from solar panel or wind turbine. Sometimes the most effective energy-saving solution comes from working with nature itself. Every degree of cooling provided by SAFE, every reduction in heating demand created by natural insulation, and every improvement in air quality achieved by living vegetation indirectly reduces electricity consumption. In this sense, the forest covering the tower becomes a form of course in direct energy generation and course, lowering the building overall energy needs before electricity has to be produced. Today, Bosco Verticals has become one of the world's most celebrated example of environmentally responsible design. Architects, urban planners, and government from around the globe studying an innovative approach as cities search for new ways to combat climate change, reduce carbon emissions, and improve the quality of urban life. More than just architecture must be. Bosco verticals prove that the future of sustainable construction may not depend solely on advanced technology. Instead, it demonstrates that by combining renewable energy systems with the timeless power of nature, modern buildings can become healthier, more efficient, and more harmonious with the environment than ever before. Part C. Village Center, the building that produces more electricity than it uses in the heart of Seattle, Washington, USA, stands one of the world's most remarkable examples of sustainable architecture, the Village Center. Often described as one of the greenest commercial buildings ever constructed, the Village Center was designed with a bold and ambitious goal to prove that a modern office building can operate without relying heavily on conventional energy sources by producing more electricity than consumed. Rather than simply reducing the environmental impact, the buildings were created to become a positive contributor to the surrounding community, demonstrating what the future of sustainable construction can truly look like. Completed in 2013, the Village Center immediately attracted international attention for its innovative approach to energy efficiency, water conservation, and environmental responsibility. Every aspect of the building was carefully planned to minimize resource consumption while maximizing renewable energy production. Instead of viewing sustainability as an optional feature, the architect and engineer treated it as a foundation of the entire project. Perhaps the building's most recognizable feature is the expansive rooftop solar array. Covering nearly the entire roof is a large collection of high-efficiency photovoltaic panels specifically designed to capture as much sunlight as possible throughout the year. Although Seattle is famous for its rainy weather and cloudy sky, careful engineering and advanced solar technology allow the Village Center to generate impressive amount of clean electricity even under less than perfect conditions. The rooftop solar system serves the building's primary source of power throughout the day. Sunlight is converted directly to electricity that supplies lighting, computer, office equipment, elevator, ventilation system, and many other essential building operations. Every kilowatt-hour generated by solar panel reduces dependence on fossil fuel-generated electricity while lowering greenhouse gas emissions and operating costs. One of the most extraordinary achievements of the Village Center is its ability to produce more electricity than it consumes during favorable conditions. On bright sunny days, the solar array often generates the surplus of renewable energy that exceeds the building immediately needs. Instead of allowing the excess electricity to go away, the building exports it back to the public electrical grid. In effect, the Village Center functions not only as an office building but also as a small renewable power plant that contributes clean energy to the surrounding community. This concept, often referred to as a net positive energy building, represents one of the highest standards in sustainable architecture. Unlike conventional buildings that remain permanent consumers of electricity, a net positive building becomes an active participant in the energy system, generating clean power that benefits both its occupant and neighboring property. This approach demonstrates how commercial building can help strengthen local energy infrastructure while reducing the need for electricity generated by coal, natural gas, or other fossil fuel. However, renewable electricity generation alone does not explain the building center. Remarkable performance. Producing more energy than a building consumes is only possible because the building has been designed to require remarkably little energy in the first place. Every component has been optimized to maximize efficiency and eliminate unnecessary waste. Natural daylight plays a central role in the strategy. Large windows allow sunlight to penetrate deep into the interior, dramatically reducing the need for artificial lighting during daytime hours. Careful building orientation and architectural design ensure that workspaces receive abundant daylight while minimizing excessive heat gain. Employees enjoy bright, comfortable offices illuminated primarily by natural light rather than electricity. When artificial lighting required, highly efficient LED fixtures are used out of the building. Motion sensors and occupation detector automatically switch lights only when rooms are occupied and turn off when spaces become vacant. Additional daylight sensors continuously adjust lighting intensity according to the amount of sunlight entering the building, ensuring that no electricity is wasted. The building center also incorporates exceptionally efficient heating and cooling system. Rather than relying on conventional air conditioning methods, the building uses advanced ventilation technology, superior insulation, and carefully engineered thermal system to maintain comfortable indoor temperature with minimal energy consumption. Operable windows allow occupants to enjoy fresh outdoor air whenever conditions permit, further reducing dependence on mechanical climate control equipment. Water conservation is another defining feature of the building as sustainable design. Rainwater falling onto the roof was carefully collected and stored for various building uses appropriate treatment. This system significantly reduces dependence on municipal water supply while making productive use of one of Seattle's most abundant natural resources. Advanced filtration technology ensures that collected rainwater meets strict quality standards before being utilized. The building center also incorporates innovative wastewater treatment and water recycling systems that radically reduce freshwater consumption. Water is carefully managed throughout the building to ensure that every drop is used efficiently as possible. Low plumbing fixtures, efficient appliances, and intelligent water management technology further minimize resources consumption while maintaining excellent performance per occupant. Even the building material reflects a commitment to sustainability. The environmentally responsible construction material was selected to reduce harmful chemicals, improve indoor air quality, and ensure long-term durability. The design emphasizes products with low environmental impact throughout the entire life cycle. from manufacturing and transportation to maintenance and eventual recycling. One particularly unique feature of the build-centric is the encouragement of healthy lifestyle. Instead of placing elevator at the center of building, the architecture design an attractive, naturally lit staircase that encourages occupants to walk between floor and whenever possible. This simple architectural decision reduces elevator use, saves electricity, and promotes physical activity among employees. The Bullitt Center has become international symbol of what is possible when renewable energy, intelligent engineering, and thoughtful architectural design are combined into the single vision. It's proof that commercial office buildings do not have to be major consumer of energy or contributor to climate change. Instead, they can become highly efficient systems capable of generating clean electricity, conserving water, minimizing waste, and supporting healthier working environment. Today, architects, engineers, government and environmental organizations around the world look to the Bullitt Center as a model field for the future of sustainable construction. Its success demonstrates that building can evolve beyond merely reducing the environmental footprint. They can actively create positive environmental benefits by producing more electricity that it consumes, recycling valuable resources, and operating with extraordinary but efficiency. The Bullitt Center offers a compelling glimpse into a future where building has the potential to become a clean energy to producer and essential part of the more sustainable world. Part 7. The technology that allows buildings to generate their own electricity, transforming an ordinary building into a solar-powered power plant and course require much more than simply installing a few solar panels. Modern energy generating buildings rely on a combination of advanced technology that work together as one intelligent system. Each technology plays a specific role in producing, storing, managing, and conserving energy, allowing the building to operate with a far greater efficiency than traditional structure. By integrating multiple renewable energy sources with a smart management system, today, buildings are becoming increasingly capable of meeting their own energy needs with reducing their dependence on conventional power grid. The most widely used technology is photovoltaic PV solar panel. These panels contain semiconductor material that converts sunlight directly into the electricity through the photovoltaic effect. Installed on rooftop, building facades, or even integrated into architectural elements, solar panels quietly generate clean, renewable energy throughout the day without producing greenhouse gas emissions or air pollution. As solar technology continues to improve, modern photovoltaic systems have become more efficient, more affordable, and capable of generating significant amounts of electricity even under partially cloudy conditions. Another important source of renewable energy is wind power. Buildings located in areas with consistent airflow can incorporate wind turbines to capture the kinetic energy moving air. Some skyscrapers are specifically designed to channel natural wind between towers, increasing wind speed and improving turbine performance. As the blades rotate, generator converts mechanical energy into electricity that can be used to power lighting, elevator, ventilation system, and other building operation. Wind energy complements solar power because it can continue producing electricity during cloudy weather and in many locations throughout the night. One of the newest innovations in sustainable architecture is building integrated photovoltaics. Instead of placing solar panels only on rooftop, engineers have developed special glass panels that contain photovoltaic cells within the window or exterior facade. These transparent or semi-transparent solar windows allow natural daylight to enter the building while simultaneously generating electricity. As cities become increasingly crowded and rooftop space become more limited, photovoltaic glass offer an efficient way to transform entire building surfaces into renewable energy generator without compromising architectural design. Closely related to this technology, a transparent solar panel, which can be installed directly onto a window while maintaining visibility. Although this system currently generates less electricity than conventional solar panels, ongoing research continues to improve their efficiency. In the future, millions of windows on office towers and residential buildings could become invisible power generators, dramatically increasing the amount of renewable energy produced in urban environments. Many advanced buildings also utilize geothermal and energy systems beneath the earth as surface. Temperature remains relatively stable throughout the year. Geothermal heat pumps take advantage of constant underground temperature to provide highly efficient heating during winter and cooling during summer. By exchanging heat with the ground rather than relying solely on conventional heating and air conditioning equipment, geothermal systems significantly reduce electricity consumption while maintaining comfortable indoor environment. Another emerging technology is the energy generating flooring, sometimes called kinetic flooring. These specially designed floor panels capture the mechanical energy produced when people walk across them. Every footstep creates a small amount of the electricity that could be stored or used immediately to power nearby lighting, display, or electronic devices. Although each individual step generates only a small amount of energy, busy locations such as airports, train stations, shopping malls, and sports stadiums can collectively produce meaningful amounts of renewable electricity from thousands of daily visitors. Generating electricity is only part of the challenge. Modern self-powered buildings also require effective battery and energy storage systems. Since solar panels produce electricity only during daylight hours and wind conditions constantly change, battery store excess renewable energy generated during periods of high production. This stored electricity can then be used at night during cloudy weather or whenever renewable energy generation temporarily decreases. Advanced battery technology increases energy independence while improving the reliability and stability of building operation. Perhaps the most important technology connecting all these systems is artificial intelligence (AI). Intelligent energy management software continues to monitor electricity production, weather forecast, occupancy level, battery capacity, and real-time energy consumption throughout the building. Using this information, the AI automatically determines when to store electricity, when to renewable power directly, and when excess energy should be supplied back to the public grid. It can also optimize heating, cooling, lighting, and ventilation to ensure that no energy wasted. By making thousands of automated decisions every day, artificial intelligence significantly improves the overall efficiency of modern energy producing buildings. Together, these technologies created a highly integrated ecosystem where renewable energy generation, intelligent management, and efficient resources use work hand in hand. Instead of depending entirely on traditional electricity supplied by distant power plants, modern buildings are becoming increasingly capable of producing, storing, and managing our own clean energy. As the innovation continues to expand, solar power buildings are expected to play a central role in creating smarter, greener, and more sustainable city for the future. Part A. The future of solar power building. The rapid development of renewable energy, artificial intelligence, and smart building technology is transforming the future of architecture. Experts believe that within the next few decades, buildings no longer function merely as places with believe work or conduct business. Instead, they will become intelligent energy hubs capable of producing, storing, managing, and selling clean electricity. Rather than existing as isolated structure cannot connected only electrical grid, future building will operate as an active participant in an integration energy ecosystem, helping entire city become more resilient, efficient, and environmentally sustainable. One of the most exciting developments is the emergence of smart energy network, often called smart grid. In this system, every energy producing building can communicate with neighboring building and a national power grid in real time. If one office tower generates more electricity than it needs on sunny afternoon, the surplus energy can automatically be transferred to nearby apartment building, school, hospital, or commercial center that require additional power. Instead of allowing renewable electricity to go unused, entire neighborhoods will be able to share clean energy efficiently through intelligent digital networks. Electric vehicles will also become essential parts of this new energy system. Future buildings are expected to include a large number of e-recharging stations located in parking garages and underground parking areas. During daylight hours, electricity generated by rooftop solar panel or wind turbine can be used directly to recharge electric cars. In some cases, pulse vehicles may even function as temporary battery storage system, returning electricity to the building or the power grid during periods of high demand. This two-way exchange of energy could dramatically improve the stability of future electricity network while accelerating the transition to cleaner transportation. Another important advancement will be an ability of buildings to automatically switch between multiple renewable energy sources. Artificial intelligence will continuously monitor weather conditions, electricity prices, energy demand, and battery capacity. If sunlight decreases because of heavy cloud cover, the building can instantly increase its reliance on wind energy, geothermal system, or store battery power. When renewable generation exceeds demand, Excess electricity will be stored for later use or supplied to neighboring buildings. This intelligent balancing system ensures maximum efficiency while minimizing waste. Large-scale battery storage will become increasingly important as battery technology continues to improve. Future buildings are expected to incorporate high-capacity energy storage systems capable of powering central operation for several days during emergency or extended power outages. Hospital, emergency response center, community facility, and residential building could continue operating independently even when severe storm and natural disaster interrupt the main electrical grid. This increased energy resilience will become one of the defining characteristics of sustainable city. As small cell power buildings are constructed, they will work together to support national electricity system that rather than placing a traditional strain upon them during periods of high renewable energy production. Buildings can contribute electricity to grid, while during time of unusually high demand, they can permanently rely on stored energy instead of draw additional power from conventional power plants. This balanced relationship will improve grid stability, reduce the need for fossil power generation, and lower greenhouse gas emissions across entire region. The vision of future smart city extends far beyond individual buildings. Millions of energy generating homes, offices, schools, shopping centers, and public facilities could form a vast decentralized network of renewable energy producers. Together, the intelligent building which created cleaner air, lower electricity costs, improve energy security, and significantly reduce global carbon emissions. Rather than depending solely on massive centralized power stations, tomorrow cities may generate much of their electricity locally through the combined efforts of countless cell power buildings working together. Part 9. Conclusion. Whenever building becomes sources of green energy, cell power building represent one of the most remarkable achievements of modern architecture and engineering. They demonstrate that technological innovation and environmental responsibility can work hand in hand to create a more sustainable future. These buildings are no longer simply that where people live, work, or conduct business. Instead, they are evolving into intelligent systems capable of generating, storing, managing, and efficiently using their own renewable energy while minimizing the impact on the planet. Throughout this journey, we have seen extraordinary examples from around the world. The Edge in Amsterdam showcases how artificial intelligence and solar energy can rapidly improve energy efficiency. The Bahrain's World Trade Center proof architecture can harness the natural power of wind through giant integrated turbines. Voice over the car demonstrate that nature itself can become a central component of energy-efficient building design. While the Building Center illustrates that modern buildings can even produce more electricity than they can consume. Together, these remarkable projects reveal a common vision for the future, a future in which buildings actively contribute to environmental protection instead of simply consuming valuable natural resources. The technology behind the achievement continues to advance at extraordinary pace. More efficient solar panels, transparent photovoltaic glass ladder battery storage system, intelligent energy management software, geothermal heating, connected flooring, and smart electrical grid are making solar power building increasingly practical and economically attractive. As renewable energy technology become more affordable, the innovation will likely move from exceptional demonstration project to standard feature of everyday construction. Within the next few decades, experts believe it may become normal for newly constructed buildings to generate enough electricity to satisfy all of their own operation needs. Some buildings may consistently produce surplus renewable energy that can be supplied to neighboring communities, effectively transforming entire city into the distributed clean energy network. Every rooftop, every facade, every window, every available surface to contribute to electricity generation, allowing urban environment to function as an enormous collection of interconnected renewable power stations. Perhaps the greatest lesson offered by solar power buildings is that sustainability is no longer simply about reducing environmental damage. It is about creating systems that actively improve the world around us. By harvesting sunlight, capturing wind, utilizing geothermal heat, integrating intelligent technology, and working harmoniously with nature. These buildings demonstrate that human-created activity can solve some of the world's most pressing environmental challenges. The future of architecture is no longer defined only by high beauty or engineering complexity. Instead, it will increasingly be measured by how effectively buildings produce clean energy, conserve natural resources, reduce carbon emissions, and improve the quality of life for future generations. In the year ahead, every new building has the potential to become more than just a structure. It can become a symbol of innovation, a model of environmental responsibility, and a small, powerful green power plant hoping to build cleaner, smarter, and more sustainable cities for generations to come.